SwayamPrabha. Digital India. Educated India.
Welcome to this tutorial. Myself Manish Maurya. I am a TA of this course. In this tutorial, I will take you through few examples based on energy balance for closed system and moving boundary work. So let's start with the first question. A piston cylinder device contains 0.15 kg of air initially at 2 megapascal and 350 degrees centigrade. The air is first expanded isothermally to 500 kilopascal, then compressed polytropically with a polytropic exponent of 1.2 to the initial pressure, and finally compressed at the constant pressure to the initial state. Determine the boundary work for each process and the net work of the cycle. So here we assume air as the system, and this piston will compress this air polytropically, and this air will expand isothermally as well. So if you see whole process on a PV diagram, so from state 1 to state 2, this gas expands isothermally. Then from 2 to 3, it compressed polytropically to initial pressure, and then finally it compressed at constant pressure to the initial state. So we have to determine boundary work for each process. First we do calculation for isothermal expansion. So work in isothermal expansion is WB from 1 to 2 will be P1 V1 ln of V2 upon V1. Okay. Since here we don't know V2 and V1, we need to find this initial and final volume of air. So from the ideal gas assumption, we calculate initial volume like mRT upon P1. So mass of air is 0.15 kg. Gas constant can be taken from this table, which is 0.2870 kilojoule per kg into Kelvin, and temperature is 350 plus 273 Kelvin divided by total pressure, which is 2000 kilopascal. So this gives us V1 equal to 0.01341 meter cube. Now we need to know value of V2. So similarly we can calculate V2 equal to mR T upon P2. Since this is an isothermal expansion, so temperature will be the same. So value of M is 0.15 kg. Gas constant is 0.287 kilojoule per kg Kelvin, and temperature is 350 plus 273. And total pressure is 500 kilopascal. So this gives us V2 equal to 0.05364 meter cube. Now putting these values in the ideal gas work expression, P1 V1 ln of V2 upon V1. So P1 is 2000 kilopascal, V1 is 0.01341 meter cube, ln 0.05364 meter cube upon 0.01341. So this gives total work in isothermal expansion 37.18 kilojoule. Now we have to calculate work in polytropic compression. So in this polytropic compression work will be from the state 2 to the state 3 equal to P3 V3 minus P2 V2 divided by 1 minus N. Since we don't know information about state 3, so we need to find this P3 and V3. So this can be obtained from equation of state for polytropic process. So P2 V2 to the power n equal to P3 V3 to the power n. So we know P2 is 500 kilopascal, V2 is 0.05364 meter cube to the power 1.2. This polytropic exponent is given to us. And P3, it is said that polytropic compression is done to the initial pressure. So that means P3 equal to P1, which is 2000 kilopascal. So putting this value here, and V3 that we need to calculate to the power 1.2. So from here we get V3 equal to 0.0169 meter cube. So after plugging this value into this expression, we get W2 to 3 equal to 2000 kilopascal into 0.01690 meter cube minus 500 kilopascal into 0.05364 meter cube divided by 1 minus 1.2. So this gives us minus 34.86 kilojoule. Now finally we need to calculate work done for isobaric process, which is from the state 3 to the state first. So this will be P3 V1 minus V3, which is equal to 2000 kilopascal into 0.01341 minus 0.01690 meter cube. So this gives minus 6.97 kilojoule. Finally, we have to calculate the net work for the whole process. So the net work of the whole process will be the sum of the total work in each process. So W net will be W from the state 1 to state 2 plus work done from the state 2 to state 3 plus W from the state 3 to state 1. So this gives 37.18 plus minus 34.86 plus minus 6.97 kilojoule, which is nothing but minus 4.65 kilojoule. So this is the total work in a complete cycle. So moving to the next question. In this question, 1.5 kg of water that is initially present at 1 megapascal and 30% quality occupies a spring loaded piston cylinder device. This device is now cooled until the water is saturated liquid at 100 degrees centigrade. Calculate the total work produced during this process in kilojoule. So it is said that initially cylinder is filled with water vapor mixture having quality of 30%. So if we see this process on a PV diagram, so initial state would be somewhere here because it is a mixture of water and vapor. So this state will be here, and now it is further cooled until that water is saturated. So it will cool down to this state 2, because this is a saturated liquid. So we have to calculate total work produced during this process, and here we assume that the process is quasi equilibrium. Okay, so the total work produced in this process would be area under this line. So W total will be area of this shaded region. Shaded part. So if we divide this region into part, so this will be the area of this triangle A, B, C, D, E plus area of this rectangle. So this will be the area of B, C, D, E plus area of the triangle ABE. Okay, so area of BCDE will be nothing but, if we see pressure at this state will be P1 and pressure at this state will be P2. So the total area of BCDE will be P2 into change in total volume. So change in the specific volume into mass plus area of this triangle, which is 1 by 2 AE into BE. So AE is nothing but P1 minus P2, and BE is total change in volume. So mass times change in specific volume. So this gives an expression for total work during this process. Okay, so this is our first expression. Okay. So now we need to know the value of these variables P1, P2, V1 and V2. Since initially we know P1 equal to 1000 kilopascal, so corresponding V1 can be calculated as Vf plus x Vg minus Vf. So this value can be taken from the saturated water table corresponding to 1000 kilopascal, which is here. So after plugging this value here, we get 0.001127 plus quality we know that it is 30%, so 0.3. Vg is 0.19436 minus 0.001127. Okay, so from here we get V1 equal to 0.059097 meter cube per kg. Okay, so now we have to calculate P2 and V2 for the state 2. Since the state 2 is a saturated liquid, temperature at this state would be 100 degrees centigrade. So from the saturated water table at 100 degrees centigrade, we can calculate P2 and V2. So P2 would be 101.42 kilopascal, and corresponding volume V2 equal to volume of the fluid, because it is a saturated liquid, so there is no vapor. So V2 will be nothing but 0.001043 kg per meter cube. So after putting these values in the expression 1, we get total work equal to 1000 plus 101.42 kilopascal upon 2 into mass time, which is mass is 1.5 kg, change in specific volume, which is 0.00104 minus 0.059097 meter cube. So from here we get minus 48 kilopascal meter cube, which is nothing but minus 48 kilojoule, because one kilopascal in meter cube equal to 1 kilojoule. So this is the total work in this process. So moving to the next question. A well insulated rigid tank contains 2 kg of saturated liquid vapor mixture of water at 150 kilopascal. Initially, 3/4 of the mass is in the liquid phase. An electric resistor placed in the tank is connected to a 110 volt source, and a current of 8 ampere flows through the resistor when the switch is turned on. Determine how long it will take to vaporize all the liquid in the tank. Also show the process on a TV diagram with respect to saturation lines. So here we consider vapor liquid mixture as a system, and this is the boundary of the system, and this is a closed system since there is no mass crossing the boundary, and it is given that 3/4 of the mass is in liquid phase. That means quality of this mixture is 25%, which is 0.25. Okay, so it is desired to determine how long it will take to vaporize all the liquid in the tank. Since it is given that tank is rigid, okay, that means volume is not going to change during the process. So if you see the whole process on a TV diagram, so initially it is a mixture of liquid and vapor with a quality of 0.25. The initial state would be here. Now it is heated, and it is heated such that all the liquid is in vapor state. So now this is our state 2 and this is our state first, and it is occurring at constant volume since it is a closed rigid tank. Now further we need to determine the time it takes to vaporize all the liquid. Since it is a closed system, so energy balance on the closed system will be total energy in minus total energy out equal to change in total energy of the system. Since this tank is well insulated, so there is no energy coming out of the system. Only energy in will be here equal to change in total energy of the system. Since system is stationary, okay, so delta Ke and delta Pe will be 0. Delta E system is nothing but change in internal energy Ke plus Pe. So these parts are 0. Only internal energy of the system will change, which is mass times change in specific internal energy. And energy in is nothing but energy coming out from this resistor, which is V times current into delta T. So the total energy during this interval will be Vi delta T. So we have to find this delta T. So for that we need to know U2 and U1, and we know V and I. So initially it is given that initial pressure is 150 kilopascal. So we know initial pressure is 150 kilopascal. So corresponding internal energy can be calculated as U1 equal to U of the fluid plus X time U Fg. Okay, so it is given here UF is here, this one, and UFG is nothing but Ug minus Uf. So UFG is this one. So U1 will be 466.97 plus quality, which is given as 0.25, and into UFG, which is 2052.3. So this gives us 980.03 kilojoule per kg. And corresponding specific volume can also be calculated as V1 equal to Vf plus X time Vg minus Vf. So Vf is given 0.001053, which is here in this table, this point and this point. So 0.001053 plus 0.25 into 1.1594 minus 0.001053. Okay, so this gives us 0.20905 meter cube per kg. Okay, so now we need to know internal energy and specific volume at state 2. So since it is given that volume is not changing, so V2 will be equal to V1, okay, which is 0.29065 meter cube per kg. Okay, we have to calculate internal energy at this state. Okay, so internal energy can be calculated at this given specific volume from this table. We don't have internal energy corresponds to this specific volume exactly, so we have to interpolate the internal energy between these two volumes. So after interpolating internal energy in between these two values, we get 2569.73 kilojoule per kg. So this is the internal energy at this specific volume. So after plugging these values in the energy balance, which is Vi delta T equal to mass times change in internal energy. Okay, so delta T will be equal to m U2 minus U1 upon V into I. So after putting these values, m is 2 kg, it is given, U2 is 2569.73 minus 980.03 upon 110 volt into 8 ampere. And since 1 kilojoule per second is equal to 1000 volt into ampere, so this gives total time equal to 3612.95 second, which is nothing but 60.22 minutes. So this much time it will take to vaporize all the liquid in the tank. So let's move to the next question. An ideal gas contained in a piston cylinder device undergoes an isothermal compression process which begins with an initial pressure and volume of 100 kilopascal and 0.6 meter cube volume respectively. During the process there is a heat transfer of 60 kilojoule from the ideal gas to the surroundings. Determine the volume and pressure at the end of the process. So here is the air compressed in this piston cylinder device. So this is the boundary of our system. Okay, so since this is a closed system, because there is no mass crossing the boundary of the system, so energy balance for this closed system will be total energy in minus total energy out equal to change in total energy of the system. Okay, so energy in will be from the work done by this piston on the cylinder. So that work in is the energy coming inside the system, and since it is losing its energy to the surrounding, so that becomes our Q out, and delta E of the system will be changing total internal energy because system is stationary. So delta KE and delta PE will be 0. So since this is an ideal gas, so delta U will be mCV delta T, that is T2 minus T1. Okay, so from here we get, since this is an isothermal expansion, so this will be 0 because T2 equal to T1. So from here we get W in will be equal to W out, that is total work done on the system is equal to total energy coming out of the system. So we know isothermal work done WB in is nothing but the PdV work from the step 1 to 2, which is P1 V1 ln of V1 upon V2. So this is work done during this isothermal compression. So this gives us V2 upon V1 after rearranging this exponent of minus W work in upon P1 V1. Okay, so from here we know that WB is equal to Q out. Okay, so plugging this value here, minus Q out upon P1 V1. Okay, so now since we know Q out is 60 kilojoule, so V2 upon V1 equal to, it is given in the question that energy coming out of the system is 60 kilojoule, so this is minus 60 kilojoule upon initial pressure is 100 kilopascal and volume is 0.6 meter cube. So this gives exponent to the power minus 1 So from here V2 will be equal to 0.3679 times V1. Okay, and V1 is 0.6 meter cube. So 0.3679 into 0.6 meter cube. So this gives V2 equal to 0.221 meter cube. So this is the final volume. We need to find the final pressure of the ideal gas as well. So that can be found from the ideal gas law. So from the ideal gas law, P1 V1 upon T1 will be equal to P2 V2 upon T2. Okay, so P2 will be P1 times V1 upon V2. Okay, because this is an isothermal process. So P1 is 100 kilopascal. V1 by V2 is nothing but 1 upon 0.3679. So this gives final pressure equal to 272 kilopascal. Coming to the final question. Air is contained in a piston cylinder device at 600 kilopascal and 927 degrees centigrade and occupies a volume of 0.8 meter cube. The air undergoes an isothermal process until the pressure is reduced to 300 kilopascal. The piston is now fixed in place and not allowed to move while a heat transfer process takes place until the air reaches 27 degrees centigrade. First, we have to sketch the system showing the energy crossing the boundary and the PV diagram for the combined process. Second, for the combined process, determine the net amount of heat transfer in kilojoule and its direction. Assume air has constant specific heats evaluated at 300 Kelvin. So first we have to draw this sketch of this system. So initially, air is contained in a piston cylinder device at 600 kilopascal. Okay, temperature is 927 degrees centigrade and volume is 0.8 meter cube. It is said that air undergoes an isothermal process until the pressure is reduced to 300 kilopascal. That means air will do some work on the piston and it will lose its pressure to 300 kilopascal. So that means it will lose its energy to the surrounding as well. It is also said that after some time piston is not allowed to move. That means after some time piston is not moving. Okay, it is constant here. So the volume of this system will not change. So this is the sketch of the system. So if we see the whole process on a PV diagram, so it is said that it is initially expand isothermally from a pressure of 600 kilopascal to a pressure of 300 kilopascal. Okay, then it is cooled at a constant volume. So let's say this state is state 1 and this is state 2, and it is cooled at its constant volume at some state. So this is our state 3. In the second part of the question says that the net amount of heat transfer in kilojoules. So we need to determine the net amount of heat transfer. So for that, this is a closed system. So for closed system, energy balance would be like E in minus E out equal to changing energy of the whole system. Since there is no heat coming inside of this system, so that means energy in is 0. There are two things crossing the boundaries of the system, that is Q out and the work done by the system on the surrounding, which will be equal to change in total internal energy of the system, because system is stationary. So total change in internal energy of this system will be nothing but mcv delta t, T3 minus Tn. Here we assume that this air behaves as an ideal gas. So from here we get minus q out equal to net work done by the system plus change in internal energy. Okay, so we know this is the total work done by the system. Since process undergoes an isothermal expansion from the state 1 to state 2, and then it goes an isochoric process from the state 2 to 3. So total work W B out will be W from the state 1 to state 2 plus from the state 2 to the state 3. So this is an isochoric process, so the work done will be 0 because volume is constant. The only work is done by the system is during the isothermal expansion. Okay, so isothermal expansion work for an ideal gas will be MRT ln of MRT1 ln of V2 upon V1. Okay, but for an isothermal process, V2 upon V1 equal to P2 upon P1. So from here WB 1 to 2 will be MRT ln of P2 upon P1. So in this expression we don't know mass of the air initially present in the system. So from the ideal gas equation we can calculate the mass of the air P1 V1 upon RT1. Okay, so after plugging the values of P1 V1 and RT1 we get 600 kilopascal initial pressure. Volume is given that 0.8 meter cube. The value of R for air can be taken from the ideal gas table, which is 0.287. So R is 0.287 kilopascal. We have to convert this unit according to numerator units. Okay, so kilopascal into meter cube upon kg into Kelvin times temperature, which is 1200 Kelvin. Since initially air is at 927 degrees centigrade. So this gives 1.394 kilogram. Okay, so total work will be 1.394 kilogram into R 0.287 kilopascal into meter cube 1 kg into Kelvin, and initial temperature is 1200 Kelvin into ln of P2 by P1. Okay, so 600 kilopascal to 300 kilopascal. So from here total work will be 332.8 kilojoule. Okay, so now plugging this value into the energy balance equation. So from there we get minus Q out equal to work done, which is 332.8 kilojoule, plus change in internal energy, so mcv delta T. So m is 1.394, cv of the air can be taken from this table which is listed here, 0.718, so that can be used here. 0.718 kilojoule per kg into Kelvin, and delta T is 300 minus 1200 Kelvin. Okay, so this gives total heat coming out of the system is 568 kilojoule. So this much amount of heat will come out of the system. So here we will stop. We will meet you in the next tutorial. Thank you.